sheet titled Newton's Laws, A Beginner's Approach. Really a very basic sheet on Newton's laws subsequent to those small little things that we've done in the class. Only to that extent. But let's start looking at some of these things together. All right. You could interact with me. You could suggest. Let's examine the sheet. Newton's laws, a beginner's approach. Right, so part A of the sheet is about, some basic free body diagrams applying F equal to ma in very ordinary situations. That's what the first part, that is part A of the sheet, is all about. The first problem of this is about a mass m, and there are two strings. This is string C, and there is this string referred to as D. They are made of the same material, and D is pulled on steadily. There is a force F applied at the lower end of D. All right. Now this is a string. It's inextensible. First of all, if I'm pulling the string steadily, right, this mass will remain unaccelerated, right? This mass will remain unaccelerated. That means it'll be essentially in a state of equilibrium at all times, right? Now, there would be tension in this string, there would be tension in this string, right? If I have to draw the free body diagram of M, then what are the forces acting on M? There is tension because of string C, let me call it Tc, which is going to pull M upwards, right? Tension in string D, which is going to pull M downwards. And there is Mother Earth acting this way, mg, right? Under the influence of these forces, the mass m is in equilibrium. Yes or no? So, can I not say that Tc must be equal to Td plus mg? Can this be said? Right? Very clearly at all times. So as I go on increasing Td, Tc will also increase. But Tc will be larger than Td at all times. Tc therefore larger than Td at all times. A string has its breaking strength. A string, even though it's inextensible, doesn't mean that you can keep pulling it forever and expect it to not snap. It'll snap. There is a breaking strength which is related to the material of which the string is made of. So this portion and this portion, they are made of the same material. They will have the same breaking strength. Suppose the breaking strength is 100 newtons, right? Which one will reach 100 newtons first? This or this? C will reach 100 newtons first. Therefore, which would be more prone to breaking? C. So C will break first for sure. C will break first. The string C will break first because the tension in the string C is larger than the tension in the string D. It will reach its breaking strength earlier than string D. All right? So string C will break first compared to string D. All right? Problem 2. There is a uniform rope of length L. When I say uniform, what does it mean? Same mass per unit length at all places. The mass per unit length is the same. See, if I take a unit length here, or I take a unit length here, or I take a unit length here, then it will have the same mass, right? So if L is the length of the string, and it's being, and let's say lambda is the mass per unit length, and I apply a rightward force F on the string, then I want to be able to calculate the tension in the rope, tension at this interface, which is at a distance x from this end. At a distance x from this end, I want to be able to compute the tension. Now, at this cross section, there is tension in both directions, right? There is tension T like this, there is tension T like this. And when I look at the entire rope, this T is an internal force and will cancel off, right? But so essentially this T that you see is pulling this portion of the rope, and this T that you see is pulling this portion of the rope, right? So this portion of the rope will experience this T, whereas this portion of the rope will experience this T. Now, in order that I could compute T, I should be able to partition the rope here and look at the free body diagram of the left portion or the right portion, right? Anyone would do. But even before that, let me look at the free body diagram of the entire string, entire rope, right? Under the influence of a force F, it will have a rightward acceleration. The total mass of the rope is going to be lambda into L, lambda per unit length into L. So then the acceleration because of this force on the entire rope is going to be F by mass, which is lambda L. That's the acceleration of the rope. And every segment of the rope has the same acceleration, right? So let me look at this portion of the rope. Let me draw the free body diagram of this portion of the rope. So if I draw the free body diagram of this portion, then the forces acting, the free body diagram of this would be a force F to the right, right? And a force T to the left. If I had drawn the free body diagram of this portion, then there would be only one force, which is T to the right, right? Now, under the influence of these two forces, what would happen? This portion will have the same acceleration A to the right. This will have an acceleration A to the right. And if the length of this is x, then what's the mass of this? Lambda x is the mass of this. The net force is F minus T. F minus T is the net force, right? And that must be equal to lambda x into acceleration, mass into acceleration, which is F by lambda L. Mass of this portion into acceleration of this portion, which is F by lambda L. Yes or no? Right? Lambda will get cancelled. Very clearly, T then turns out to be F into 1 minus x by L. Very clearly, tension is a function of x here. If the rope has mass, the tension will be a function of x. However, like I mentioned in an earlier session, if the rope is inextensible as well as massless, light that is, then the tension will be the same everywhere. Then the tension will be the same everywhere. Right? Now, just to make sure, just to make my assertion believable that T could have been computed by using the free body diagram of this as well as this. Now let me take the free body diagram of the left portion and see if I end up getting the same value of T or not, right? So now this portion, the portion to the left, is of what length? L minus x, right? So now the free body diagram of this portion is going to be, which is of length L minus x, is going to be, there is a force T to the right on this portion. The tension perceived by this portion is going to be T to the right. And under the influence of this will have the same acceleration A to the right as before, right? So then, applying Newton's second law to this segment, what is it that I get? T equal to mass of this portion, which is lambda into L minus x is the mass of this portion, into acceleration A. Acceleration A is F by lambda L. T then is F into, if I divide by L, 1 minus x by L. Yes or no? Right? That's the same as what we got earlier. Now there are these blocks resting on a smooth surface. And there is a force F which is applied. We want to determine the normal reaction between M2 and M3. The force that M2 exerts on M3. Right? That's what we want to be able to find. Now, even before that, if I just draw the free body diagram of M1, M2 and M3, then that will include a force F to the right, then gravitational forces M1G, M2G, M3G downwards, and the normal reaction from the ground which would balance these gravitational pulls. Right? No vertical acceleration means they will cancel off. Right? So I'm not going to delineate the vertical forces. They are not having any impact in the motion. Right? So now if I have a force F to the right, then, and if I look at the free body diagram of all these, then the forces that they exert on each other at their interfaces would be internal forces and will not find any representation, right? So free body diagram of M1 plus M2 plus M3 is this, along with M1G, M2G, M3G and upward reactions on each one of them, right? The acceleration A is going to be F divided by M1 plus M2 plus M3. Now, if I look at the free body, now if I want to find the forces that M2 and M3 exert on each other, what would I have to do? I would have to rupture them at the interface so that that force gets exposed, right? So let me look at the free body diagram of M3 alone, for example. So if I looked at the free body diagram of M3 alone, now what I know is the effect on M3. M3 has the same acceleration as M1, M2, M3 so as to maintain contact. So the acceleration of M3 is known, A, which we have computed from the free body diagram of the entire unit, right? Now, in which direction will M2 exert a force on M3? Rightward. Normal forces are always pushing in character, right? So M2 will exert a normal reaction N on M3. And what would this N do to M3? It will provide M3 an acceleration A to the right. So can I not say N must be M3 into A? Right? So N, the required force must be M3 into A, which is M3 into F divided by M1 plus M2 plus M3. Right? Could I have also looked at the free body diagram of M1 and M2? Let me just look at that for the heck of it. Right? That way also N will get exposed. But so far so good, right? Let me look at the free body diagram. So this was free body diagram of M1 plus M2 plus M3. This is M3 alone, right? Let me look at the free body diagram of M1 plus M2. Now, there is going to be a force F. What else? No. Don't see, please understand. Cause and effect. Acceleration is not a force. It's the cause of the force, right? So don't mix it up. No. If M2 is exerting on M3 N to the right, M3 will exert on M2 N to the left, right? That same N that we computed earlier now. We are trying to compute using the free body diagram of M1 plus M2. Then of course there is M1G, M2G balanced by upward reaction, so I'm not representing that. Okay. And what's the net effect of these forces on M1 and M2? An acceleration A to the right. Right? So of which we have knowledge. This time we have knowledge of the effect. We want to find the cause. The cause are the forces, right? So can I not say F minus N is M1 plus M2 into A? Now A you can plug in as computed earlier and obtain n. From these considerations you will get the same value of n. You know what I'm saying? Could I have looked at the free body diagram of M2 alone? Now that I have computed n, right? I could have looked at what would be the free body diagram of M2 alone? M2 alone. M2. M3 will exert on M2 n leftwards. And M1 will exert on M2, say N1 rightwards. And the net effect of this would be A to the right. N we have computed. Right? I can now compute N1. So can I not say N1 minus N is M2 into A? N has been computed earlier and N1 could now be computed from these considerations. Right? So just feel comfortable with these very basic free body diagrams and play around, tinker with them at ease. So far so good, right? Not a problem? We have a trolley here. There is a pulley and a mass M2. Mass M1 and the mass of the trolley is capital M. And a force F is applied on the trolley. Now, we want to find the value of F so that the blocks remain stationary with respect to the cart. The two blocks remain stationary with respect to the cart. There is no relative motion between M1 and capital M and M2 and capital M. There is no relative motion. We want to be able to find the value of F commensurate. Alright, which means all the three masses have a common acceleration. If there is no relative motion between the masses, any pair of masses, that means all the three masses must have the same acceleration. Yes or no? What? So let's say all the three masses have an acceleration A to the right. Do I have knowledge of the value of A now? What would A be? If I looked at the free body diagram of the three, then what they did to each other, the tension, etc., will all be internal, will not be factored into this free body diagram, right? Right. So A is going to be the net force F divided by M plus M1 plus M2. That's going to be A. Now, if I have to look at the free body diagram of M2 alone, what would be the free body diagram of M2 alone? Tell me, what are the forces acting on M2? M2G downwards. And there is going to be tension upwards. Is there any other force? Yes, there is. Yes, capital M will exert on M2 a normal reaction N to the right. What is the net effect of all these forces acting on M2? Acceleration A to the right. M2 has the same acceleration A as capital M to prevent relative motion, right? Yes, but why should that capital M will tell? Why should M2 tell you of that? If I am drawing the free body diagram of M2, then M2 will only reveal the what is happening to M2, not to what it is doing to capital M. If I had to draw the free body diagram of capital M, then the force on capital M will get exposed, right? No, it is not.
Then T is equal to
Yes, yes, exactly. Since M2 has no vertical acceleration, which is what I was coming to actually. N of course must be m2a and T must be equal to m2g. If that was not the case, then m2 would have had a vertical acceleration and there would be relative motion between capital M and small m. You know what I'm saying? Okay, so T must be m2g. Now, if I have to look at the free body diagram of m1, what's the free body diagram of m1? There of course m1g downwards. There is normal reaction from the cart upwards. And there is tension to the right. Same tension. And tension will always pull. And what's the net effect of all of this? Acceleration a to the right. Because capital M has an acceleration a to the right, m1 must also have an acceleration a to the right. Right? So can I not say T is also equal to m1a? Can I not say T is also equal to m1a? Right? So T, which is m2g, is also equal to m1a. Yes or no? And do we have knowledge of A? A is F by capital M plus M1 plus M2. That must be equal to M2G. So capital F must be this into this divided by M1. Capital F is what we needed to compute, right? So capital F turns out to be M2G by M1 into capital M plus M1 plus M2. That's the value of the force that will prevent relative motion. That will prevent relative motion. Got me? Yes or no? These are elements, you just need familiarity with these elements so that you know. Eventually, let me tell you, any complicated problem on mechanics will only require multiple applications of these simple elements that you're learning. You know, whenever you see a complex situation in mechanics, it's not complex. It's actually putting together of several simple situations of this kind only. And therefore, you know, we want to actually go through these simple situations so that, you know, complex only looks simple appearing multiple times. That's what complex turns out to be, right? Huh? But simple, isn't it? No issues with all of this? Are you all right with this? This is a fixed inclined plane. And these are two blocks passing over a pulley, two pulleys, and connected to another identical mass, capital M as shown. Everything resting on a smooth frictionless surface, but this is known to be fixed. All right. We want to find the tension in the string. We want to be able to find the tension in the string. Now, there are two ways of looking at it. Let me look at it by drawing free body diagrams of these two masses. All right. So if I have to draw the free body diagram of this mass capital M, then realize that this mass capital M experiences mg downwards, right? And this mg we could resolve. See, if this angle is theta, this will be theta, right? I hope you are all familiar with this geometry. This would be mg cos theta. This would be mg sin theta. And there is going to be T upwards, isn't it? And is there any other force acting on capital N? Anyone? Yes, there is. There is normal reaction from the inclined plane. Capital R acting like this. There is normal reaction from the inclined plane, capital R. in this case, since the inclined plane is fixed, and this mass has no acceleration in a direction perpendicular to the plane, right? Because if this mass had an acceleration perpendicular to the plane, then there would be relative motion in a perpendicular direction, and that will result in loss of contact, right? So in this case, r is mg cos theta, but this is the complete free body diagram. R may not always be equal to mg cos theta, by the way, right? If the inclined plane was not fixed, then that will not be the case necessarily. Realize that. R may not always be equal to mg cos theta. If the inclined plane is fixed, then r is mg cos theta. It is not always true. We'll come to those situations. Let's go past some of these simple things before we can embark on learning some of those things as well, right? But in this case, r is mg cos theta because the block has no acceleration perpendicular to the plane. Now, under the influence of all of this, the block has an acceleration a parallel to the plane. It will move only parallel to the plane, right? That's a constraint. So what's the equation of motion for the block? Mg sin theta minus t must be capital M into a, right? So equation of motion for the block is mg sin theta minus t equals capital M into a, right? Now let me draw the free body diagram of this block on the horizontal surface. This block on the horizontal surface is capital M, which of course has mg downwards, balanced by a normal reaction R1 from the ground upwards. There is tension T acting to the left. What's the net effect of M? Now, do you realize one thing? See, if this moves down the plane by 1 centimeter, this will move to the left by 1 centimeter. Why? To maintain constancy of string length. That's a string constraint. So if I assume that this has an acceleration a parallel to the plane, then this must have an acceleration a parallel to the ground, commensurate with constancy of string length. Inextensibility of string is what guarantees this. This is not the force that this is exerting on the ground, by the way. Mg is the force that Mother Earth is exerting on capital M. Please understand this. This is not the force that this is exerting on the ground. It is exerting R on the ground. It so happens that R is equal to mg, but mg is the force. These are external forces acting on capital M. Mg, I repeat, 2050 times. This mg is not the force that capital M is exerting on the ground. This is what Mother Earth is doing to capital M. Yes, right? And this ground will exert a force R1, normal reaction, pressing force on M1, right? And R1 in turn would also be the force that capital M exerts on the ground if you have to draw the free body diagram of the ground. This capital Mg is not the force that the mass exerts on the ground. Repeat that. Tell me. Right. Good. Of course it does. When did I say it will not exert? But this is, when I draw the free body diagram of capital M, will I show the force that this is exerting on other bodies, or will I show the force that other bodies are exerting on this? What will I show? Other bodies, now. So now if I have to draw the free body diagram of the surface, now this R1 is the force that the surface exerts on M. M in turn will exert on the surface a force R1 like this, commensurate with Newton's third law, right? Please draw a very clear-cut distinction. Don't mess it up, all right? And ask questions. This initial stages, you might ask questions of this kind, but feel free to ask so that at least, you don't stay confused. Huh? Okay. So does this not summarize all forces acting on capital M? Now, in absence of vertical acceleration of capital M, R1 must be equal to mg. So don't bother about that. T is the one which is instrumental in providing capital M an acceleration a leftward. So can I not say T must be capital M into a? T is inconsequential for me. I'm seeking to find a. I'm seeking to, T is consequential, I need to find T. But either I can divide this by this and find T, or what I could do is T is MA, and this ma I could write as t. This ma I can write as t, so 2t is mg sine theta, t is mg sine theta by 2. Either way you want to solve it. Now, only for the heck of it, you know, I want to demonstrate one more thing in this connection. The problem is solved, right? A will be g sine theta by 2, A will turn out to be g sine theta by 2, and so on and so forth. Now, can I remove the clutter from here and just demonstrate another fact? See, if I didn't need t and if I just needed acceleration without involvement of t, you know, I could have, think of it like this. I open up the whole system. I open up the whole system and I could think of as if there is an mg sine theta acting on this, opening it up. Just mentally imagine it to be opened up. That will be equivalent, right? And there is this string, no matter what, it passes over a pulley, but eventually gets connected to the mass capital M. Capital M. Now, this is the free body diagram of capital M and capital M together along with the string. In which case, I'm bypassing what the string is doing. Because the tensions in the string, if I looked at the free body diagram of capital M and capital M, would be internal. Will not seek any representation, right? Now, on this capital M and capital M, this is the only external force then, right? The acceleration of the system then is going to be total force mg sine theta divided by the total mass, which is 2m, which is g sine theta by 2. Got me? You could do that. You know, this opening up thing is for our mental comfort, right? Don't get cynical about, you know, why I have done it, but effectively it could boil down to this. Effectively it could boil down, and a similar thing could be done in pulleys as well, just to bring that to your notice also. Do you understand what I mean? This is the equivalent that I can imagine for a quick reckoner, quick computation of acceleration. If I didn't need the tension, I just needed the acceleration of the two masses, then this acts as a ready reckoner, right? This would work. And a similar thing in case of pulleys. Can I wipe this off? Yeah, which is what it is, right? Yes, it is. Both the masses have an acceleration a. This along the plane, whereas this along the horizontal. So this is, I gave you a more authentic solution earlier, but this could be used as a ready solution, a quick one for acceleration. You know, in pulleys also, if this is a fixed pulley, there is M1G, there is M1, so there is M2. And without involving the tension, if I want to be able to find the acceleration of the system. See, one thing for sure, if M1 has an acceleration a downwards, like we saw in the earlier class, M2 would have an acceleration a upwards. And they must have the same acceleration in a simple situation of this kind for the sake of inextensibility of the string, right? Now, without drawing the free body diagram of M1 and M2, if I directly want to find the acceleration of 2, what I do is, see one thing, there is M1G acting this way, there is M2G acting this way, right? I open it up. I mentally imagine the system to be opened up, as if it's placed on, don't worry about where it's placed. It's not placed on the ground. It'll be confusing. It's as if there is M1 and M2, and there is, see, I'm opening this up. So there is going to be M1G like this, external force. There is going to be M2G like this. These are the only two external forces then. Yes or no? Right? And under the influence of these two external forces, what would be the acceleration? The acceleration is going to be M1G. Net force to the left, say the acceleration is A to the left, m1g minus m2g divided by, that's a ready reckoner. That's a ready reckoner. I could have otherwise drawn the free body diagram of the two masses separately, right? In the sense, for m1, the equation of motion would have been m1g minus t equal to m1a, right? Now t acting on this, the free body diagram of m2, which is t minus m2g equal to m2a. Equation of motion for this, t minus m2g is m2a. Now if I add these two equations, then I get m1 minus m2 m2g equals m1 plus m2 into a is what I get. A then turns out to be m1 minus m2 into g by m1 plus m2, which matches with that result, right? But instead of drawing the free body diagram of m1 and m2 separately, I could have looked at them together, mentally conceived the whole system be opened up like this, and without involving tension, because if I look at m1 and m2 together, tension then renders itself as an internal force, and I could have directly computed A as m1g minus m2g by m1 plus m2, which is the same as that result. Got me? Where there is a ring in a vertical plane, this is a ring in a vertical plane. These are two perpendicular diameters, vertical and horizontal. There is a bead here, and the two beads A and B are joined by an inextensible cord, a wire. They are constrained to move on this frictionless ring. The blocks are released from the beads, in fact, are released from rest. We want to find the tension in the cord just after the release. That means just after this moment, what would be the tension in the cord? That is what we are seeking to find here. All right. Now, one thing, A and B are at rest. And the points A and B on the bead will always move along the circle. So their velocities will always be along the tangent to the circle, right? Isn't it? Now, very clearly, right after release, A would develop a tangential velocity which is horizontal, B will develop a tangential velocity which is vertical, right? Which means there would be an acceleration of A along the tangent right after release, call it A1, horizontal, and there would be an acceleration of B right after release, which is acceleration A2, which will also be along the tangent. Yes or no? The net axis. Let's see that. Give me a little while before I finish, Let's understand why A1 will be equal to A2. Now, this is a string. And realize that this angle is 45 degrees. This angle is 45 degrees. Yes or no? It's an isosceles right angle triangle. This is 90 degrees, so this will also be 45 degrees, ordinary geometry. Now, if you look at A and B like this, A and B, the string remains taut. That means the separation between A and B is not going to change with time. The string remains taut. That means the separation between A and B is not going to change with time. Now, the acceleration of B is, say, A2 like this. Acceleration of A is A1 like this. Very clearly, their relative acceleration along AB must be 0. their relative acceleration along AB must be 0, commensurate with inextensibility of the string, right? Now this is 45 degrees. This is also 45 degrees. That means if their relative acceleration along AB is 0, component of acceleration of A along AB must be the same as component of acceleration of B along AB. What's the acceleration of A along AB? A1 cos 45 degrees, right? What's the acceleration of B along AB? A2 cos 45 degrees. And they two must be equal. Why? Inextensibility of the string. Their relative accelerations, their relative velocities along AB must be 0, right? So, which causes A1 to be equal to A2. So, for sure, right after release, the acceleration of the point A on this bead would be along a horizontal tangent. Acceleration of point B is going to be along the vertical tangent. Yes or no? Now, A and B, let's say the two beads have identical beads, so have the same mass, right? Now, if I have to look at the free body diagram of A and B separately, let me look at the free body diagrams of A and B separately. If you think of A, this is the end B. A will experience, there is tension in the cord which is T. A will experience a force T like this, right? And this T would have a horizontal component which is going to carry the horizontal acceleration and will have a component which is like this. But since the bead has no vertical acceleration, it has only a horizontal acceleration, the wire, the circular wire must exert on the bead A a force N like this, so that the vertical component of T and N could cancel off. Vertical component of T and NA could cancel off, so that A at this instant doesn't have a vertical acceleration. Do you realize that? T cos 45 degrees must be equal to NA, so that at this instant the vertical acceleration of A is 0. Yes or no? Okay, now there is, of course, mg also like this, but don't bother about that. There is the net effect of all of this is an acceleration A. A1 equal to A2, let's say each is equal to A. So can I say this is 45 degrees? So can I say T cos 45 degrees must be MA? Right? Horizontal acceleration is caused by the horizontal component of T, which is T cos 45 degrees, right? And the vertical forces T sine 45 degrees, mg and NA would cancel off, right? So then, can I say T cos 45 degrees is MA? Is MA? That's as far as bead A is concerned, right? Let me look at bead B. Let me look at bead B. Again, bead B has a vertical acceleration A. There is going to be tension T acting on bead B like this from B to A, pulling in character. Now, do you also understand that this T has a horizontal component acting on B, but B has no horizontal acceleration? So there must be the wire exerting on B a force N like this, a force N like this, right? It must exert a force NB like this, so that the horizontal component of T could get cancelled, preventing a horizontal acceleration of the bead B. Yes or no? And then there is mg acting this way for bead B, right? Under the influence of all of this, bead B has a downward acceleration A, right? So then there is this angle 45 degrees. So can I say mg minus T mg minus t must be m into a, mg minus t cos 45 degrees must be m into a. Can I say this? mg minus t cos 45 degrees must be m into a. Can this be said? Right? Now if I add these two, then I get 2ma is mg, or a is g by 2. Yes or no? Got me? Okay, but we need to calculate t. We need to calculate t. So if I know a, which is g by 2, then from this equation, t cos 45 degrees, t into 1 by root 2 must be m into a turns out to be g by 2, or t then turns out to be mg by root 2. The tension T which we are seeking turns out to be mg by root 2. Clear? You could, some of you would have got the right answer the wrong way, the wrong answer the right way. Okay? You would have not conceived, I do not know if there is anyone who conceived of the problem completely. Did you think of all the normal forces and the direction of accelerations of A and B completely, or you just managed to get mg by root 2 by hook or by crook? Partially. Okay. Let's look at problem. But is this understood now? Okay. So here we have two wedges. Block A and block B. Mass m each, and they maintain contact. This is their interface. This is their common interface. And this angle is given to be 30 degrees, right? This angle is 30 degrees. There is a force F applied on capital M, and there is a force 2F applied on this small m. Oh, both are small m actually. Okay. And the block A, there is no relative motion between A and B. That's given. And they maintain contact. We want to find the normal reaction between A and B. This is what we want to find. We want to find the normal reaction between A and B. Now, first of all, if I look at A and B together, then the forces that they exert on each other, will that find any representation? No. Why? Because that's going to be an internal force, right? Now, if I look at the free body diagram of A and B together, then these are the two external forces along with Mother Earth and reaction from the ground, and I don't bother about those vertical forces. They are inconsequential in this situation. So then, the net effect of these two forces acting on the composite block is an acceleration A, which is going to be 2F minus F, right? F, 2F minus F, F divided by 2m is the acceleration. Yes or no? Now I seek to know what is happening at this interface. So if I seek to know what is happening at their interface, I will have to act wicked. I will have to cut this open here, right? I would have to create a partition and then look at the free body diagram of A alone or B alone. That's the only way I can expose what is happening at the interface, right? So let me look at the first things first. B exerts on A. See, this is their common normal. B will exert on A a normal force N like this. A will exert on B a normal force N like this. Action-reaction pair. Right? Now if I have to look at the free body diagram of A alone, then the free body diagram of A alone is like this, with a force F acting, and this angle 30 degrees, right? And B will exert on A this N, right? B exerts on A a normal force N like this, right? Now, see, if this surface makes an angle 30 degrees with the horizontal, perpendicular to this surface will make an angle 30 degrees with the vertical. Yes or no? If a given surface makes an angle 30 degrees with the horizontal, then the perpendicular to the surface will make an angle 30 degrees with the vertical. Yes or no? So this makes 30 degrees with the vertical. Right. Now, look, and there is of course mg acting downwards. There is normal reaction Ra acting upwards. Does this summarize all forces acting on this block? All forces. All forces. Acceleration is not a force, it's an effect. So the effect of all of this is known to us, which is an acceleration A to the left, right? Now, what causes A? N sine 30 degrees minus F. Isn't it? N sine 30 degrees minus F must be M into A. Isn't it? N could have been resolved as N cos 30 degrees vertical, N sine 30 degrees horizontal. So can I say N sine 30 degrees minus F is M into A? Could that be said? Right? So N sine 30 degrees minus F is M into A. A we know. M into A is F by 2. Isn't it? See, M into A is F by 2. This F transposed on this side. N sine 30 degrees means N by 2. F plus F by 2 is 3F by 2. N then turns out to be 3F. Yes or no? No issues with this? Which is about, say, a balloon. Mass M means mg acting downwards. It's displacing air, so it's going to experience a buoyant force F. Weight of the air displaced, it experiences a buoyant force Fb. Under the influence of these two forces, it's known to have an upward acceleration of g by 6. Right? So the equation of motion for is Fb minus mg is mg by 6. So that gives us Fb equal to 7 mg by 6. Right? Now, next what is done is, there is water which is put inside the balloon. We are assuming that it's not going to affect the volume of the balloon. If it's not going to affect the volume of the balloon will experience the same buoyant force, right? So, same buoyant force, and with capital M as the mass of water added inside this, plus M, that's the total mass, that's M plus M into G. And what we are seeking is, by adding capital M units of water, what we are seeking is an acceleration g by 6 downwards. Now the fresh equation of motion is m plus small m into g minus Fb is equal to m plus m into g by 6. Fb you can plug in as 7 mg by 6 and solve for capital M. Is this what you did? What did you get capital M as? 2m by 5.